exponential numbers, like square root of blah 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 plus another square root of omega equals something simple, for example. Well, it is conjectured that the only way in which you can move from one period to another, given by one to another integral, is through manipulations of the integral of an analysis kind. So changing variables, splitting it into different subdomains. So that's the only type of relationship that can exist between periods. And that's sort of like the previous conjecture that I told you about multiple zeta functions, which are supposedly related to each other only through those subtle products and their natural generalizations. So that's right. But I'll look it up and I'll tell you tomorrow if the previous paper contains one number that is not the previous concrete. So again, there are conjectures on gamma being the product and maybe the Euler point. Thank you very much for your invitation. It's a pleasure to be here in such a comfortable and welcoming place, in such a joyful country. You know, last night when I waked up a little after midnight, I was very much impressed how people in this country are so prompt to celebrate the French National Day. But all right, very happy. Today, I'm sorry for this very mysterious talk, at least my talk, but hopefully not talk. Essentially, I'm going to talk about nonlinear PDEs and harmonic analysis, and harmonic analysis is related to Hankel operators. And my purpose will be to show you how using in an unexpected way Hankel operators and spectrum theory for these Hankel operators, which are well known in harmonic analysis, can help in understanding different issues in nonlinear PDEs, in particular the question of weak turbulence issue, namely transition to high frequencies. So this is a joint work with Sandrine Lallier for the main and first part, and for the second part, which is more recent, with Zhang and Tally. Okay, so I should first explain what is my nonlinear PDE here. It's very simple, and as you will see, it's a context framework which is quite familiar to people in harmonic analysis. So I'm starting with the Hardy space, which I see as the subspace of two functions on S1, namely functions which are L2 on the circle and which are only negative Fourier forms. Okay? And this space, of course, can be as well we've seen as a so-called Hardy space on the disk, namely the function which are homomorphic on the unit disk with L2 Fourier coefficients, or L2 for coefficients. Okay, so on this space, or this space is associated with a well-known orthogonal projector which consists in forgetting the negative Fourier modes in the Fourier decomposition of any function L2, and this I will call the Singer at-risk projector. People call it the Singer projector. Too many things are called for this. Okay? So, and the equation I'm interested in is just this one. So I'm looking at functions which depend on the time and on the variable on the circle or on the disk, let's say the circle here, and which satisfy the following equation. I of 1u squared u. Okay, so this we call the cubic Singer equation. So from the viewpoint of Hamiltonian systems, it's a very simple system. Essentially, you look at the following energy function, E of u equals 1/4 of the integral of S1 of u4, and you think of it as an energy on this space S2 plus. Okay, it's a down-bounded energy, but still, okay. And then, even though S2 plus with the vertical symplectic form, which is is the imaginary part of the N2 inner product. And then, if you look at the Hamiltonian evolution associated to the system, you get that. And the pi is here because you have to, of course, you take the gradient of this guy, but then you have to on the phase space, which is F2 plus. So why are we interested in this equation? Okay. So there are many reasons, but let me give you 3 reasons why I find it interesting to look at this equation. The first reason is really related to nonlinear PDEs. Remember that this is not precisely a PDE, except that if P means pseudo-differential. Okay. But the more classical PDEs are, for instance, nonlinear Schrödinger nonlinear wave equation in this context, and this is in fact the point model for large time behavior of a nonlinear wave equation, certain nonlinear wave equation. Nonlinear wave equation. So I will not discuss this today, but during the same workshop on, remember, Thursday maybe? Yes. Thursday, for another topic, we'll talk about this nonlinear wave equation and related things to this Segur equation. The second reason is that this is a very simple equation. The main problems we are faced with in nonlinear PDEs, which is understanding the interaction between nonlinear operations like U square U and non-local operations such as pi, so non-local pseudo-differential operator. And here this is really a selection of equations. Yes, they just select non-negative equations. So in some sense, the whole difficulty is concentrated in just one term, and we would like to know how it affects the dynamics. So pi, non-local, but linear, and U square U, local but non-linear. And the third reason, which is of course probably the main one, is here that there is something hidden in this equation. It's integrable. And the definition of integrable is you can write the solution. Okay, with the formula. Complicated formula, but you can write the solution. And okay, maybe you know a little bit about some examples of integrable nonlinear equations. Maybe the most famous one is the Kostelet-Leibniz equation. And you could say, okay, but for these equations, the large time behavior, at least from the viewpoint of transition to high frequencies, as I spoke in the beginning, is essentially trivial because there are many conservation laws, so many that they control the whole solution. So it's a classical patch. But this is not the case here. So this is an integrable, but some kind of new kind of integrable equation because the conservation laws, there are many conservation laws, okay, but the conservation laws do not control regularity, high regularity. So in some sense, the conservation laws are many, but they are weak. Okay. So these are the 3 main reasons. Now, what are we interested in? Well, we are essentially interested in the dynamics, large time dynamics. And of course, first you need to define the dynamics, and the global dynamics are defined because of some conservation laws. So it's very easy by an inspection of the structure I briefly described in the beginning to find 3 conservation laws. So the first one is of course the energy law, which is the L4 law, the fourth. The second conservation law is the L2 square law. Well, this corresponds to the action of multiplication by complex numbers of modulus 1. They act on the equation, they act on the whole structure. So by Noether's theorem, this is a conservation law. And there is a third conservation law, which is also related to the action of a one-parameter group, which is just rotation on the circle. Okay? And the conservation law here is the so-called momentum. It's u. Okay. So we have 3 conservation laws. Now we are very lucky in that case, because if the UU, if you compute what it is, and maybe I will add here's the square norm, I have something like this. Sum from k equals 0 to infinity of 1 plus k u path of k squared. Just by reminding you that the spectrum of u is on non-negative modes. So this is a positive and a definite positive quantity, and this is essentially the h-half norm square. So we are very lucky because this is conserved, and since we are in a one-dimensional equation and h-half is in one dimension is very close to infinity, not exactly, but not so far, okay, we can use some classical tricks in nonlinear PDE and prove that we can. This fact, which is already known, we proved with something that a couple of years ago, is that for every s at h equal to half, you have a global remoteness of the Cauchy problem on the phase space space with S regularity, so let me call it HS. So this H is not the same as here, this is some of it, if I may. If HS plus of 2, which is the classical Sobolev space of the circle intersection with S plus. Okay? So those functions which are HS on the circle and which only have non-negative Fourier modes. So you can define a nice global flow on all these spaces, and you see that in the case of S equals a half, the norm is essentially a constant by this conservation. Now we would like to know about the dynamics of all these spaces. And it turns out that there is a dramatic difference between S equals a half and S bigger than a half, and this is my main result. So this is a theorem that we proved, in a different way. In fact, the first theorem is due to myself and something Xavier a year ago. And it tells you that if I'm starting from data in the biggest one, in this energy space, H1/2 plus, then I know a lot about the solution. The solution that by U of t satisfies that the mapping which is associated to every real time the solution U of t in the Hilbert space H1/2 plus is an almost periodic mapping. So we have a very nice evolution, almost periodic, corresponding to what we expect for some integrable system. Now the second point, which is certainly more surprising, concerns the case S bigger than a half. And then this is a theorem we proved with Zayatani, and it was just a couple of weeks old. And it tells you that for every S bigger than a half, there exists a dense G delta subset in HS plus, such that for any initial data in this dense G delta subset, the solution U is unbounded in HS plus. So in other words, you have some growth of Sobolev norms for generically on the initial data in HS, or S bigger than a half. So it's far from being almost periodic, of course, it's even not bounded. Okay? So I would like to tell you about not the whole proof, but how angle operators enters into proving such a theorem. Okay, so for that, of course I need to prove the raised port, and then to tell you the connection with harmonic analysis and angle operators. So it's a very old and classical subject in harmonic analysis, so I'm going to remind you, maybe to the youngest of you, the main questions of the main definition of angle operators, and we will see very, very soon how it's protected. So what is an angle operator? An angle operator so we work on the Hilbert space on sequences with non-negative additions. Space, I'm given a sequence C called Cn, and I look at the operator gamma C, which sends N2 into N2 under some conditions I will specify later on Cn, and sends the sequence Xn onto the sequence, the sum from t equals 0 to infinity of Cn plus t xt. Okay, so in other words, we have the following matrix, which is a semi-infinite matrix on the canonical basis of L2, and this matrix is made of coefficients which are constant on all anti-diagonals. Okay? So this is n plus t equals constant, and for n plus t equals constant, the coefficient here is constant. So this is an angular matrix. Now, it's a very classical result due to Z in Harry at the end of the fictive, tells you that gamma C is a bounded operator if and only if, well, there exists a U in an infinity of S1 such that Cn is U hat of n for all n, not negative. Okay. Of course, you can have different choices for U because this only characterizes the Fourier coefficients of U for n not negative. Now you would like to have U in our N2 plus space, but then it's not possible in general. And you have then, for U in N2 plus, you have then to replace N infinity by pi of N infinity. And this is not N infinity, this is well known. And about 10 years after this theorem, it was proved by Charles Zimmermann that this is the same as DMO. Okay, DMO plus, by the way. DMO intersection with N2 plus. So essentially, if you think of the Fourier series with the coefficient Cn, this operator is bounded if and only if the Fourier series is in DMO. Okay? Now, there is in fact another and much simpler result of continuity, which is that gamma C is in fact much more than bounded, it's Hilbert-Schmidt. Well, if Hilbert-Schmidt is very easy to see, if and only if the kernel, which is here Cn plus P, is on L2 on both variables. But this, because L and P are non-negative, is equivalent to have this property. Sum of L plus 1 Cl plus Cl squared is finite. And now if you think that Cl as you have of L, L non-negative, and forget about the negative variables, then this is equivalent to the fact that U is H half plus. So these Hankel operators are, I think the Hilbert-Schmidt operators are connected to our space H half plus. Okay. Now, the main result is the following integrable structure that I will write in two different manners. Well, essentially, it tells you that if U is a solution to our cubic Sego equation, our nonlinear PDE, then there are some spectral quantities related to the corresponding Hankel operator, which are constant, which are conservation. So the theorem is as follows. We prove this with something Gallier. It tells you that if U satisfies the cubic Sego equation RU dot equals pi of U square U, then the singular values of gamma U hat and the singular values of gamma U hat dot plus 1, so you shift the Fourier sequence. All these singular values, this is a Hilbert-Schmidt operator, so of course it has, if you look at the gamma star, it's a set-adjoint trace class operator, so it has plenty of eigenvalues, and the singular values are just the square root of these eigenvalues, so they are conservation rules. So this is the theorem. Now, maybe to tell you a little bit about this theorem, it's better in fact to adopt a different realization of these Hankel operators acting on our space L2 plus. Of course, L2 of G plus is isometric to L2 plus by the Fourier transform, Fourier series, and I say that in fact you can transport the whole structure of L2 plus. If U is in H1 plus or in DMO plus, I define HU on L2 plus, the following operator which sends H onto pi of UH bar. So I need absolutely this bar, so I take the complex conjugated extension, so it's not a linear operator, it's R-linear, but it's not C-linear, it's anti-C-linear. But we have the very nice property that if you look at the Fourier coefficients of HU of H, this is the same as gamma U hat of the Fourier coefficients of H, comma. Okay. So in particular, if you look at HU squared is, by the Fourier transform, is equivalent to gamma U hat. And then you can play the same game with introducing the shift operator on L2 plus, which is just a multiplication by C on monomorphic trenches, or by E to the IX on trenches on the circle. So you just put a 0 in front of the Fourier decomposition, and then you introduce the following operator KU, which is S star HU, and also HUS, and also H S star U. And in that case, you have exactly the same property that KU vet H hat is gamma U hat dot plus 1 of H hat bar. So you can transfer everything onto L2 plus. It's much more convenient because in this context we can prove the following result, which clearly implies the one I stated. Okay. And which is a classical structure in infinite dimensional integrable structures, which is called a Lasch-Spare structure. So what is a Lasch-Spare structure? So in this very particular case, it's rather easy to write. So this is a precise theorem. Lasch-Spare for the cubic Sego equation. So I claim that if U satisfies the cubic Sego equation, IU dot equals pi of U squared U, then I can write the evolution of these two operators, HU and KU, I just defined. The derivative of HU is given by the bracket of HU with some operator DU, which is completely explicit. DU of H equals minus pi of 1u squared h plus I over 2 hu squared of h. Okay? And we can continue with the same result for ku. Let me write it down just to show you how it changes. In fact, it changes very, very little. So dku dt as well is given by the commutator cu ku. We have cu of h equals minus pi of u squared h plus I over 2 hu squared of h. Okay, so the observation is that these operators du and cu, for all time, they depend on the solution, of course, and they depend on time. They are perfect anti-Sephardic, sorry, because there is anti-Sephardic operator. They are linear.